well-designed experiment. Designing a statistical experiment is not just about collecting data, it's about planning carefully so that the data we gather truly answers the questions we are asking. A good design controls variation, reduces bias, and ensures that results are both valid and reproducible. Hi guys, I am Dr. K. Muralidharan, a senior professor of statistics working with Maharaja Sayajirao University of Baroda. In this video, I will explain how experimental designs can be constructed statistically. Okay, look at the statistical models. A statistical model is a mathematical framework that represents the process by which data are generated using probability theory. So y equal to f of x1, x2, etc. xn plus epsilon. So x1, x2, etc. xn, they are the inputs or the factors, and y is the dependent variable, and epsilon is the error term. So you can see that randomness, that epsilon comes with randomness. There it's also called a stochastic term or dynamic term or nuisance term, disturbance term. There are a lot of names associated with epsilon. And that's because of the randomness. And randomness plays a very important role in statistical decision making. And all studies are based on random samples. So most of the time, if you see, especially statistical inference, we always talks about all inferences based on samples. An ideal sample is that which takes care of complete representation of events. And both probability and non-probability random sampling methods can be used for data collection, and that is generally discussed in the classroom teaching of sampling. A designed experiment facilitates data collection and its analysis efficiently, and that is the most important aspects of design of experiments. Why a designed experiment? Experiments can be designed in many ways to collect the information. However, a strategically planned and executed experiment may provide a great deal of information about the effects on a response variable due to one or more factors. And that's what I had already shown you in the form of y equal to f of x1, x2, etc. xn plus epsilon. A well-designed experiment is that which is as simple as possible for obtaining the required information in a cost-effective and reproducible manner, because DOE is considered to be an expensive tool of statistics. So design of experiment, or designing an experiment, statistical experiment, even any experiment, if you look at a chemistry-based experiment, physics-based experiment, experimentations are very, very expensive. So naturally, DOE is considered to be one of the expensive tool of statistics. Okay, let us see what are the components we need. For any experiment to design, we need three basic components. What are the inputs and experimental units on which you are going to experiment, and the outputs called the responses or data. So you have a response, that is y, dependent variable, output variable, and input that called treatment or factors. That's what the usual terminology of design of experiments. And then you look for constructing a model in y in terms of xi's. In a statistically designed experiment, data is obtained through the study of cause and effect relationships. You can see here y is the effect, and x1, x2, etc. they are the causes. But they are used in a controlled method. So since it's an experimentation based, so you need to see the different settings which impacts the effect y. So let us look at a simple example. A nutritionist invented a new diet plan which he believes to reduce 5 lb body weight in 2 weeks. So he experiments this plan to his overweight uncle for 2 weeks and observes the reduction of 5 lb in weight. So you can see very well that the diet plan is the treatment here. So that is what is your input, and the nutritionist's uncle becomes the experimental unit, and the body, the weight reduction becomes the response. So data is, that's what we are finally looking for. Okay, so the question is this a design experiment? I'm sure that you will be thinking about it. I'm sure that you will get the answer also that it is no, because there is no control. Okay, there is no comparison with any other treatment. That's why it is not. There's only single treatment and single person. There is no randomization, nothing. So even if you experiment this, the reduction in weight can be due to some other factors also. Okay, maybe due to physical work, or maybe some other food plan, food control, or something like that. Similarly, there is no randomness in the allotment of treatments, because here the diet plan is applied to a subject with choice. Okay, most of the time, make sure that this experimentation involves people not by choice but voluntary participation, because if you see the clinical trial experiments, medical experiments, etc., so people are invited voluntarily. So if there is a consent only, then you go ahead. And of course, the third problem is replication of the treatment. The data plan is applied for only one person. Okay, so that's another issue here. So definitely the above context is not suitable for a design. Okay, let us see. So this clearly says that the experimentation needs three important components. They are control, randomness, and replication. If that is there, you can say this is a well-designed experiment. When such a design experiment is performed, the output of the experiment will become automatically random. So that's why we need in statistics, we need always a random data. Okay, if without any variation data is coming, there is no meaning. There is no further study required here. The experiment can be designed by various designs depending on the objectives and given okay, given outputs as well as inputs. Okay, there are a lot of designs which is generally discussed in statistics. So starting from completely randomized design in the basic design, and randomized block design, lattice square design, so one way, two way, three way, like many mixture distribution, complex designs, nested factor response surface designs, etc., etc. So for a beautiful account of that, you refer to design of experiments by Montgomery. Okay, let us now start with a simple experiment. How the previous context can be explained through a one-way analysis of design. Okay, so in a completely randomized design, the name itself suggests it is randomization is done nicely. Okay, experimental units are assigned randomly to groups. Okay, so subjects are assumed homogeneous, assuming subjects are homogeneous. Only one factor or independent variable is considered here. And the model looks like Yij is equal to mu plus tau ij, 2i plus epsilon ij. I is running from 1 to there are A treatments, and j number of samples or treatment numbers are 1 to n. So mu is the common parameter or common mean to all the treatments. 2i is the parameter unique to the ith treatment, and epsilon ij is the random error component which follows n0 sigma square. And it can be very well analyzed using one-way analysis of variance. Okay, let's look at this previous example, how that can be converted to a completely randomized design. So a nutritionist wishes to study about the effects of three types of diets, because we need a randomization, replication, and local control or simple control, or these aspects. So without that, it cannot be called a design. So we need, so three types of diets are now considered for weight reduction for obese children. So 18 children gave their consent for joining the research experiment. So completely voluntary. He wishes to design the experiment making three treatment groups of equal sizes. Yes, one can even go for unequal sizes as well using a completely randomized method. So I will explain with the equal sizes. How should he design an experiment to get a random sample? That's the first question. And how will the final output of data looks like? That's the second question. And then you can get into the analysis part. Okay, so what you need to do is simple thing. Label all the 18 children randomly from 1 to 18 with some identification mark and put it in a ball. Similarly, you take another ball with 18 identical cards where 6 of them will be labeled as dat 1, 6 of them labeled as dat 2, and 6 of them labeled as dat 3, because we have assumed equal sizes. So if you are going for an unequal sizes, you can change the number of dat 1, dat 2, dat 3 like that. Put it that in a second board, and then select randomly one from each board. Okay, and see and record the indicated dat as assigned to the indicated child. Okay, so you will get one from one board, another one, say simultaneously you can draw, or you can ask someone to draw and see what which child is given which dat. So just record it and repeat the procedure without replacement. Here the best policy is without replacement. You can also try with replacement plan as well, and then you can finally get a a data sheet of this kind. This is simply an allocation, not a final data to be analyzed. You cannot analyze this. There is no meaning in analyzing this one. This is simply the allocation. You can see that child number 2 is given diet number 3, 18 is given number 3, diet 7 is given number 1. So probably this will be more beautiful to see, to understand the data clearly. So diet 1 is given to 7, 6, 3, 14, 15, 11. Diet 2, 12, 17, 10, 1, 16, 18, and so on. Okay, so what is next? So definitely the next question is the nutritionist will work practically on the experiment for the specified duration. Okay, maybe for 2 weeks or maybe for 1 month. And at the end of the completion of the experiment, he will get the information in the form of the difference in weight, that is weight reduction. Make sure that the weight is done or the measurement of weight is carried out before starting the experiment of all the 18 candidates, and after completion of the experiment, maybe 2 weeks or maybe after 1 month, take the weight and take the difference of that 2 weeks, the initial minus the final, then or final minus initial, let it be in absolute term, no issue. And if that difference is less than 5 lb, then probably the diet plan will work. Okay, so this is how the final output is going to be, the data output. You can see the first two rows are same as the previous one, and the weight is also added to each one. So the child number 1 was given diet number 2. After the experiment, the difference in the weight is 3.7. That's how it can be interpreted. So the best way to interpret this data is now this way. So diet 1 is given to, you can see that, identify the child, and diet 1 is given to 4 point, the child 1, sorry, child number 3, then child number 6, 7, like that. So the weight reduction is 4.1, 4.3, 3.4, etc. Okay, so this is the best way of presenting the data now, which is now ready for analysis. So the objective is to test whether the average of the three diet plan has any effect on the weight reduction or not. So technically this is described as H naught mu1 equal to mu2 equal to mu3 versus they are not all same. There will be a strict inequality somewhere. So this is a statistical problem. So you can again put it in the statistical problem solving way. So you use one way analysis of variance and get the answer. So the practical problem here is, can different types of diet help reduce weight reduction of these obese children? And that is converted beautifully to a statistical problem, H0 and H1. Sorry, H1, it should be H1. And statistical solution has to be possible through one-way analysis of variance. We found the value as F value because it's a matter of testing overall significance in variances. So the variance test, we generally use F test. So F value is 0.6908 and the corresponding critical value is 3.682, and these two values are compared, and even p value is also shown here is going to be 0.52, so the test is accepted. So if p is less than 0.05, that's why generally most of the software does the job. So if p less than 0.05, you reject the hypothesis, but here it is too high, so the hypothesis accepted. So what is the practical conclusion or solution? Since we accept H0, we can conclude that there is no significant difference of evidence between the three diets. That is, for this experiment, the effects of diets are almost similar. So there is not much, difference between the diets. So that means all the diets perform, the diets are same. And probably this for this particular data, for this experiment, the data, the conclusion is coming out to be, and don't consider this to be a generalization. So if you have a different data, a different context, different experimentation, similar to this, probably you may get a different conclusion. Okay, so what are the points to focus while doing a statistically designed experiment? Fit the appropriate statistical model, that's what one always look for. It can be a linear, quadratic, response surface, etc., etc. You can look for anything, whichever you feel like where the fit is good. And goodness of fit can always assessed using R square, adjusted R square, lack of fit, etc., etc. For design of experiment, this is how we always look for. And simplify the model if necessary by removing the non-significant factors from the model and give importance to interpretations based on the test criteria. Yes, of course, we need to do that many often, because if one of the criteria accepts and one another criteria rejects, probably you may need to have a real testing the criterion as well. And identify critical factors that significantly affect the responses. Ultimately, that's what we need to do. So what is actually affecting why? Okay, what or which axis are going to be affecting the y's, and develop recommendations for process improvements. Okay, that's what is statistically needed. Okay, and stay tuned for that. Tuned for my next video on the same name, elucidation and interpretation. I am coming with another video on RBD design and plus other designs also. Okay, thank you very much.